Okay, very good. Everybody got that, or very nearly got it. Okay? We have, of course, the vector is going to be tangent to this thing, and it's y that's changing, right? And of course, k is going to be k, just as before, but it's going to be the partial derivative with respect to y. And I believe your text, if you read it, would bring that about. You know, by the time you digest what we do in here, I expect to be able to read the text pretty quickly. Not having to worry about the details, you just get an overview. Then you go back to the text for examples if you need it. And maybe you just go right to the problems, because problems are fairly straightforward, at least they start that way. And then by the end, they'll lay something important on you. Okay? So that's the way it's going to work. But and you should understand that. Anyhow, there you got two tangent vectors, right? Okay, what can you do with two tangent vectors at a point? Well, if you've got two tangent vectors, two vectors tangent to this surface, it's like, again, you've got a vector in this direction and you've got a vector in this direction, right? What can you do with those? Well, you can find their dot product if you want it, or their cross product. What's their dot product going to be? Well, what angle does this vector make with this vector? Tell me what the dot product is going to be. You signal that with your fingers. It'll be 0. Because this plane is totally perpendicular to this plane. Every vector in this plane is perpendicular to every vector in this plane. And two perpendicular vectors, well, the standard test for vectors being perpendicular is the dot product is 0. And you should understand that totally in terms of what the dot product means. And the idea of, well, if you project this vector onto this vector, your projection line is going to go right down here, and it's going to be 0. Okay? You need to have that picture. You need to understand projections completely. Because we're getting into things where you really need to use this. So make sure you have that idea. Okay, so what about the cross product? What's the significance of the cross product? Well, if I do the cross product of, let's say, this vector with this vector, it'll be like this. It's going to be normal to this surface. It's going to be perpendicular to any vector on this surface, assuming this surface is a plane, and as you let the region of the xy plane corresponding to this picture, well, what's that region? Let's just draw that region here. Okay, that's going to be a region here. Here, there's your H, there's an H. Might not be the same H, doesn't have to be, because it's going to shrink to 0. Okay? And these two things shrink to 0 independently. Right there is our region. Okay? So I can kind of put it in parentheses. And you can verify for yourself, and you should, that that region is a rectangle down in the xy plane. There's your region. Okay? Now, if you confine this region so that this thing fits within a small ball, everyday deal of a ball, in higher dimensions, okay? You shrink this thing down, then H has to shrink in both dimensions. And so I don't want to clutter this up too much, but kind of sketch a ball. It contains this region. And that's not absolutely necessary, just put it in a bigger context. Within this small region, what you have up here is just again prism, truncated prism for small h. Nearly flat here, a region within a small ball. And this region, I put a plane here, and you tested this because you measured this and you tested whether this cross product is equal to this cross product and so forth, or the unit normals that you get. We did that early. So you want to relate that to that. Okay, as this ball shrinks, then any region inside the ball is going to shrink down. The biggest region you put inside the ball is going to keep shrinking, and this top is going to get flat if you have a continuously differentiable function. And normal is just this vector crossed with this vector. So, without further ado, because we did this some time ago with measurements, now your measurements are replaced by these partial derivatives of the results of your measurements. The normal vector is K, and of course, that normal vector, you don't need a determinant to evaluate this. I cross J is just K. K cross J is just negative I. Now, I'm getting tired of writing out that whole partial derivative thing. Another notation for partial derivative, f sub x means partial with respect to partial of f with respect to x. And then I cross K is partial. Negative partial. The visualization almost left me there. I want to make sure it was negative partial just because I'm trying to be careful about little details so I don't write things down and have to fix it. So now there is your normal vector. Now it's convenient to remember this, but don't use this as a formula because this doesn't have any direct meaning. It's convenient for calculation, but the direct meaning is this. And this isn't hard to understand. So don't ever use this without thinking back to where it comes from. At least think, okay, my tangent vectors are I plus fx times k and j plus fy times k. They're perpendicular. If I take their cross product, I'm going to get the normal vector, and this is what it is. Because if you think that, you'll always be able to test yourself. Okay. So, you can think about what this means geometrically. For the picture, well, let's go back to this, okay. And let's take the, try the normal vector at this corner. Okay. So, let's put this corner here, so you have a, okay, it doesn't matter what your coordinate system is, but one of your partial derivatives will be a vector like this, and the other will be a vector that is a little bit upward, so that the cross product is back this way and tilted this way a little bit. Okay? And you want to be sure you can visualize that. This means that if the x-axis is this way and the y-axis is this way, both partial derivatives are positive. Okay? Now you have a normal vector equal to k, of course, which is this way, and then a minus fx times I. Okay. Well, the steeper this thing is here, the bigger fx is. Fx is the steepness of this vector, with the slope of this segment here. The steeper that is, the more it tilts your normal vector back this way. Okay? Because as this vector gets steeper, what happens to your thumb? It goes back this way, of course. You have this. And similarly, the steeper this is, the more you got to tilt your hand in order to match this slope. So fx tilts you back in the negative x direction, corresponding to negative fx times I, and a positive y derivative. I think I said that right. Positive x derivative tilts you back this way. Negative x direction, x partial would tilt you this way. When you do the cross product, if you have a positive partial with respect to y, you got to move your palm this way, and you get a component in the opposite direction. You know, opposite, in the y direction. Okay, I don't have a good syntax for that sense, and I'm not even going to try. Okay, but that's your negative fyj. You want to understand that all visually, and you want to keep thinking about it and think about it. Don't just grind out an answer and hope it's right to a question about a normal vector. Think about it. Now sometimes, of course, it all comes out in symbols. Still, think about this picture. If it's in symbols, you don't know whether fx is positive or negative. You don't know whether fy is positive or negative. So you don't know if it's this way or this way. You don't know if it's this way or this way. Now, what's the big deal about the normal vector? Well, if you have the normal vector, you can do the tangent plane. It's through, let's say you're doing it at this point, okay? Because that's the point we've kind of said is your x naught, y naught, or more generally your x, y. Okay, if this point is x naught, y naught, then what are the coordinates of this point? This point here. Again, that's the point directly above the point x naught, y naught, right? What's the y coordinate? It's f of x naught, y naught. So the coordinates of this point are x naught, y naught, okay, so your tangent plane is through the point And how do you do tangent plane? It's the plane through a given point perpendicular to the normal vector. And you want to be sure you understand the geometry of that. If you don't, you want to go back and review it, because the better you understand the geometry of three-dimensional space, the more things are going to make sense to you, and the easier it is to analyze more challenging problems. The better basis you'll have for analyzing challenging problems. So there we have it. There's everything you need to know about the tangent plane. Now, implicitly, this is a function that's differentiable in the neighborhood of x naught, y naught. Okay, or at least differentiable at x naught, y naught. Because if it isn't differentiable, it means that these limits don't exist. These limits are this one and this one. At least one of them doesn't exist. They don't both exist. Okay. Okay, well, that's the whole idea of a tangent plane. It's easy enough to calculate. All you got to do is be able to take the partial derivatives. And taking partial derivatives is real simple. We'll do a few examples. Also do an example of this limit, because that's what did throw some people right at the end of the homework section.